Okay, let's look now at section 14.5 and talk about the concept of surface area. So let's begin with a surface that's defined on the XYZ coordinate system. So here we have a little dome. And this dome is defined over a particular region. This is its domain. All right, so the domain is in the XY plane. And so here this function is a function of those two variables. Z is equal to f of x comma y. Okay. Now, let's say we're going to find the area of this surface. Okay, well, it's curved, and finding area is something that's simpler if your region is flat. So let's go ahead and approximate this using a flat region. All right. Here, what I want to do is I want to focus on one little square in my domain. So here, I'm going to consider this little square, and it doesn't really matter which one, but I'm going to consider this little square here. Okay. And now let's take the points inside of that little square and project them up onto our surface. Okay, so if you plug this into your function, you get a point up here. If you plug this corner point into your function, you get a point up here. So let's say you plug all of the points inside of this little square into your function, and that's going to give you some curved surface, some little patch of our surface up here. So we've taken a little tiny piece of it. Well, now this is a big curve. It's a big dome. But if you look really closely at just a really small little patch of it, the curvature doesn't really affect you very much. If you start from here and go all the way over here, there's a lot of curvature to that path. But if you just start from here and go to here, yeah, this is slightly curved, but it is mostly flat. Just like you have a sphere, like say you have the Earth, and you have something that is curved, but if you happen to have a very small little patch of it, for example, you look outside your window right now, even though you may live on a curved surface, nearby you, everything looks pretty flat, especially if you live in Texas, yeah? So this little patch can be approximated by a flat little plane. So let's take that little patch and approximate it using a perfectly flat plane, right? So we have and let me use a different color on this. Let's say I have a perfectly flat plane that approximates that. Okay. Now here, that may be a little bit hard to see, but I'm drawing a perfectly flat, perfectly square little square. Now, of course, that's just for a visual effect. But of course, notation-wise, we can represent that a little more simply. After all, the curved one, which I've drawn here in blue, is a small little bit of surface area out of the entire thing. So I'm going to have S for surface area, and I'm going to say, okay, I have a little tiny bit of it, a little tiny amount of surface area. Now here, you notice that I have a lot of little patches, each of which has its own surface area. So here I'm going to say delta S sub I, and that's just the amount of surface area of a little tiny patch right there. And that is going to approximately equal to, well, here I have a flat little plane. Well, we've seen in previous chapters that if I have a surface, I can approximate that surface with a flat plane, and that's the tangent plane. So here I'm going to say, okay, well, I can approximate this surface with a tangent plane. But again, I don't want the whole surface. I only want a little tiny bit of a surface, which means I only want a little tiny tangent plane. So this little patch can be approximated by delta T sub I. All right, and again, T for tangent plane. The I just because there's going to be multiple ones. This will be the first one, the second one, the third one, the fourth one, and fifth one, and so forth. But if there are going to be so many of them, well, then I'm going to need to add them together. Okay, so here, that suggests that if I add together these little patches, that's going to give me the total surface area of this surface. But that's approximately the same as adding together each of the little tangent planes. So that's going to be the sum of delta T sub I, like that. Okay. Now, for now, we want just a finite number of these. Of course, we know we've had enough experience of this starting since Cal 1. We know we're eventually going to take a limit. But for now, we just want this to go, okay, we want I starts from 1, from the very first one, up to some finite number, from 1 up to n. And same thing over here, from 1 up to n. So let's say I break this up into 20 little patches. Well, I can approximate the actual surface area by adding up the 20 little tangent planes at each of those 20 little patches. All right, but now where do we get these from? Okay, we're going to use this as an approximation to what we want, but now where do these come from? All right, well now let's look down to see where this came from in the first place. If you go down to your domain, here you have a little tiny patch, and this is not on a surface, it's rather on the plane. So here, if I'm measuring this, it only has two dimensions, length and width. So it's a little bit of area. All right, so we've seen the notation for that before. That's a little bit of area, a little delta A. And here again, I'll call it delta A sub I, because there's one, this one corresponds to that one, this other one would correspond to another one, and so forth. All right, well notice this is simply a little rectangle in the plane. And the way I've drawn it here, and it wouldn't have to be drawn this way, but it makes the notation a little simpler. Here I have the sides of my little rectangle parallel to the x-axis and to the y-axis. So here, the area, well, that's length times width. Well, that's just going to be a small change in the x direction for my length times a small change in my y direction for my width. Okay, so here this delta A sub I is the same as saying I'm going to take a delta x sub I and multiply it by a delta y sub I. Okay, so it's just a little rectangle. So now if we project that up into the surface, notice that this little green approximation, this little flat plane, well, this point would project to that point up there. And then to get from this point across this way, so I could find the dimensions of this little patch that approximates my surface area, so that I could find the dimensions of delta Ti, all I'm doing is I'm saying I'm traveling along these two side lengths. But again, these are parallel to the x-axis and to the y-axis. So that means if I take one of these vectors here, here, let me just write this off because the drawing's getting a little cluttered here, so that I can give the area of delta Ti, that's simply going to be a length times a width. After all, it is a little rectangle. All right, but now if I want my length times my width, that's going to be this side vector and this side vector. All right, so let's say I start with this one right here. Well, this is only along the direction of the x-axis, which means the y component is nothing. So here, I'm going to say, all right, that's a vector going this way. And that's going to be, well, only along the x direction. And we said the amount we're moving along the x direction is a little amount, little delta x sub I. We're not moving in the y direction for this one, so that's going to be 0, the second component. And the third component, we've seen in previous sections that if you're taking a small step in the direction of the x-axis, the z changes by an amount that's equal to the partial derivative with respect to x. Saying that a slightly different way, I'm at a point, I'm walking only along the x direction. The amount that my function will change is, by definition, the partial with respect to x. So here, this third component would be f sub x, the partial with respect to x, again at that particular point. So this would be xi comma yi. Okay? So that's going to be one of my vectors. And then I'm going to go ahead and find my other vector in the opposite direction here. And that's just going to be, well, same thing. This only goes along the y direction, not the x direction. So that's going to be 0 for the first component. The second component, delta y sub I. And again, if I'm going along the x direction, that's the partial with respect to x. Now I want to go along the y direction, which means that the change in z will be given by the partial with respect to y. Okay, but now you say, okay, so I'm going to multiply these. Okay, well, remember, we have more than one kind of multiplication. There's the dot product and the cross product. Well, recall from chapter 11, we saw that if you have two vectors, the area that is bound in a parallelogram whose adjacent sides are those two vectors is simply given by the cross product of these two. And you say, well, that can't be right. The cross product would give me another vector. Here I'm looking for an area. Areas aren't vectors, they're scalars. Right, so we take the magnitude of those. So here, the delta t sub I, and here that's given by the magnitude of the cross products of the length and the width. So here, this is a geometric interpretation, length times width, to give you an area. But here, from chapter 11, we see that that's really done by the magnitude of the cross products. Okay, so let's go ahead and take a look, and let's do that. Here, let me actually take the cross product of those. Let's see. I'm going to do it just using this method here, ijk. Delta x sub I 0 f sub x. Here I'll leave that off, otherwise it gets really big here, cluttered up. And then I'll just repeat that, delta x sub I 0 and f sub x. And then that one's going to be 0 delta y sub I f sub y, and then I'll repeat that. Okay, so now that I can find the cross product by simply taking the four diagonals. Okay, well that's 0, so that's 0i. This one here, that's also 0. Okay, so that's 0j. And this one is going to be delta x sub I, delta y sub I. Okay, so that's the only one that's not 0. Delta x sub I times delta y sub I k. Okay, so the first two are 0. But now I'm going to say minus, and then I'll go in the other direction. Okay, well that's 0. Okay, so that's 0k, and let me write that in order. So let me write the k at the end. 0k. Here that's going to be f sub y delta x sub I. So that's f sub y delta x sub I j. And then this one, which gives me I, is going to be f sub x times delta yi. So f sub x delta yi I, like this. And now if I subtract all of those, I end up with, well, that's 0 minus that, 0 minus that, and that minus 0. So this will give us the vector, and here I'll write it in this form. The first component is 0 minus that, which is negative f sub x delta y sub I. Oh, and I apologize. I missed something here. I noticed it when I actually started to combine these. Here, f sub x is the slope of this line right here along the x direction. But if I want to figure out how far z went down, the slope isn't enough to tell me. I have to multiply the slope times the small change in the remaining direction, right? It's like if I were to say I want my slope is equal to the change in y over the change in x. Well, if I know my slope and I'm trying to find my change in y, I have to multiply on the other side by my change in x. So delta x times my slope is equal to delta y. So over here, it's not sufficient to just give the slope. It's not sufficient just to give the derivative. I have to multiply by the derivative. I have to multiply that derivative times the small change in the other direction. So here, that should be partial of x times delta x. And over here, that should be partial of y, delta y. That won't actually change what we're doing here. It will just give me one extra term, right? One extra factor in this term here. So let's see here. That would be f sub x delta xi, and same thing for this one. And this should be f sub y delta yi, and same thing for this one. So when I start multiplying here, this one hasn't changed. That's still 0. That's still 0. And that's still delta xi, delta yi. So that first one hasn't changed at all. It's this one that'll change here slightly. Here this will be f sub x delta x delta y. So here that should be delta x and delta y. And same thing for the second one. This should be f sub y delta x delta y. You know what? Let me just rewrite that. So here that'll be f sub x delta y. And that's the first component. The second component would be f sub y delta x delta y. And then the third component, that one's still 0, so that one doesn't change at all. Okay. And that was the change here. I was missing that one there. So here that will be, and I'll write this in this form, 0 minus that, well, that's negative that. So that's negative f sub x delta x I delta yi. This one, 0 minus that, is negative f sub y delta xi delta yi. And over here, that's this minus 0. Well, that just stays like that. So that'll be delta xi delta yi as my third component. Here you notice that delta xi delta yi is common to all three of these. And not only is it common to all three of these, but it can be rewritten as delta a sub I. Delta xi, delta yi, that's our delta ai. I knew that had to come up. That's why I realized, oh, I was missing that one term there. So here we can write this as minus f sub x delta ai, comma, minus f sub y delta ai. And here that would be just delta ai. Okay. All right, so there's going to be the cross product of these two vectors. That cross product, if I now take its magnitude, that'll give me the area of this little tangent plane. Okay, so let's go ahead and do that. So now we want the magnitude of minus f sub x delta ai, comma, minus f sub y delta ai, comma, delta ai, like this. And when we find magnitude, we just take the squares of each of these, add them together, and take a square root. All right, so let's go ahead and do that. We're going to take the squares of each of those. So that'll be minus f sub x delta ai quantity squared, plus minus f sub y delta ai quantity squared, plus delta ai quantity squared, and all of that's going to go underneath the square root. Right? That's how you find the magnitude of a vector. Take each of the components, square, add, and take a square root. Okay, well now that can be written as the square root of, let's see, that's going to be double negative, makes that a positive, so that's going to be f sub x delta, f sub x squared, delta ai squared, plus f sub y squared, delta ai squared, plus delta ai squared. Notice that's a common factor, which we can now factor out as the square root of f sub x squared plus f sub y squared plus 1 times delta a sub I squared. And now, even though this is something a little bit big and messy, this is a perfect square. So I can separate that and just write this as the square root of f sub x squared plus f sub y squared plus 1. And now, since I've taken the square root of this, it now appears on the outside as just delta a sub I. Square and the square root are gone. So what we get is that the delta t sub I is equal to the square root of f sub x at xi comma yi squared plus f sub y at xi comma yi squared plus 1 delta a sub I. But then that means that from our previous assertion, if we want to find the sum of the surface areas, all we're doing is we're taking the sum of these things that we just found. So we can now write that as the sum as I goes from 1 to n of delta s sub I. That's equal to the sum as I goes from 1 to n of delta t sub I, which we can write as the sum as I goes from 1 to n of all of these things, which is square root of f sub x squared at xi comma yi plus f sub y squared, again at xi comma yi, plus 1 delta ai. But if that's our approximation, that's an approximation that we're familiar with. We're taking the sum of a thing over an area. By Fubini's theorem, we can now write this as a double integral. If we pass through the limit, we can now, oh, sorry, I'm getting ahead of myself. Not Fubini's theorem yet. By definition, we can now write this as a double integral over a region R with respect to the differential A. By taking the limit as n approaches infinity of both sides, up here, take the limit over here, take the limit over here. If we let the norm of our partition approach 0, if we let the diagonals of our little patches, if we take the diagonals of these little squares, if we let them approach 0, that means that there's going to be more space to fit more of these in. So that's equivalent to saying n approaches infinity. And as the norm of our partition approaches 0, right, the smaller they are, the more fit in, we get that the, and this is an approximation there, we get that the limit as n approaches infinity of the sum as I goes from 1 up to n of delta S sub I is equal to the limit as n approaches infinity of this one, which is really the limit as n approaches infinity of this one. The sum as I goes from 1 to n of the square root of f sub x squared x sub I comma y sub I plus f sub y squared at x sub I comma y sub I plus 1 dA. Our surface area is given by this summation over an area. But we've seen this. This is a double integral over the differential A. All right? So that brings us to our theorem here. Or rather definition here. We'll see the theorems about this in the coming sections. And this definition really is just what's suggested by our previous development here. Let f be a continuous function with continuous first partial derivatives. So f should be continuous and also should its partial derivatives. Let them be continuous on a closed region R, where R is its domain. It's on the xy plane. The surface area of the surface given by z equals f of x comma y. This equation gives you some surface. We want to find its surface area over that domain. The notation for that is the double integral over R of the differential of surface area. That's basically the left-hand side of this right here. If you take the limit as n approaches infinity of the sum of delta s's, that gives you the double integral of ds. All right, that's our notation for writing this limit as a integral, in this case a double integral, since your domain is over two variables. That's going to be given by, and this is essentially the right-hand side of this, right? And that's the double integral over that same region R of the square root of 1 plus the first partial with respect to x squared plus the first partial with respect to y squared all over the area of that region with respect to A. Fubini's theorem tells us that, of course, we can evaluate this either with respect to x and then y, or with respect to y and then x. So let's take a look at an example of how this is going to work out. Let's say we wanted to find the surface area, and let's start off with something reasonably nice. Let's find the surface area of the paraboloid. Now you might say, well, paraboloids usually go on forever, right? Well, sure, but we need to bound it, right? It needs to be bound over a closed region. The entire xy plane is not closed; it goes on forever. So here, find the surface area of the paraboloid. Z is equal to 16 minus x squared minus y squared in the first octant. You'll hear this said a lot in the first octant. That's just a shorthand way of saying, oh, by the way, we want x to be greater than or equal to 0. We also want y to be greater than or equal to 0. And we want z to be greater than or equal to 0. That's what this means here. It's just like saying the first quadrant, but now instead of having things on the plane, now we have things in space in 3 variables. So our first octant is where everything's positive. All right. So now we can give a surface area by defining our region, first of all, on the xy plane, and then integrating over that region with this as our argument, as our integrand. So let's start off by defining our region R. You don't have to draw this, but I choose to do it partially because, well, it's a good way for me to convey information to you. At least I think it is. So here I have a quick sketch of this. It doesn't have to be perfect, but it's just enough to convey what it is we're looking at. So here I have a paraboloid. And of course, we've sketched plenty of these before. If you look at the traces, that's a parabola facing down with a height of 16. That's a parabola facing down with a height of 16. Right? And that is a circle of radius 4. All right? If I set x is equal to 0, that's one of my traces. That's a parabola. Because there's a minus there, that's going to be, well, maximum height is 16 and it's facing down. If I set y equals to 0, same thing. That's a parabola facing downwards because that's a negative x squared. And if I set z equal to 0, in other words, if I'm on the xy plane, I could take the x squared minus the y squared here and move them over to the other side. And that would give me a positive x squared plus a positive y squared equals to 16, which is a circle of radius square root of 16, circle of radius 4. So as a very nice, short, and quick illustration here, well, maybe not nice, but certainly short and quick, here's a maximum height of 16. We know that on the xy plane and, oh, not on the xy plane, on the xz plane and on the yz plane, we have a parabola facing down that has a height of 16 in both cases. And on the xy plane, whenever z is equal to 0, we have a circle of radius 4. Something like this. Right? So there's going to be 4 and 4 and 16. So now here we don't want the entire object. We only want it in quadrant number 1. So we want x to be positive, so this way. We want y to be positive, so this way. And we want z to be positive, so up here. So really we only want this stuff in here. We want everything from this part of the xy plane, because here x and y are both equal to positive numbers. They're greater than or equal to 0. And then we want everything above that because we also want z to be greater than or equal to 0. So really we want all this stuff here. All right, so there we go. That's what we want. This illustration also gives us our region R, because remember, R is the region over which your surface is defined. And here we want all the stuff up here. Oh, well, it's defined over that quarter circle, that quarter disk. So here, this region R is simply on the xy plane. Everything that's above the x-axis, everything that's to the right of the y-axis, and it's the quarter circle in this region, which has a radius of 4. All right, so there's our region R. And that'll help us set things up. Okay, so if that's our region R, then I can describe this region so that I can integrate with respect to its area. All right, remember by Fubini's theorem, we can either write this with respect to y first and then x, or with respect to x first and then y. Here I'll just do y first and then x. It doesn't really make a difference here. So here I'm going to say, okay, the double integral over r ds, or in other words, my surface area, is going to be given by Fubini's theorem. Instead of writing this as a double integral over r, I can write it as the iterated integral, first with respect to y, then with respect to x. Again, by Fubini's, this order doesn't matter, but once you establish the order, then you have to be careful to describe your boundaries correctly. Right? If you wanted to start with x first and then y, that's fine too, but again, you got to be careful to describe the region appropriately. All right, well now y I need to describe the extreme values of y, and here I'm allowed to use either constants or any variable that hasn't been used yet. Or in other words, I'm allowed to use x as well. Okay, so describing my y values using either constants or x variables. Well, my y values always start from down here. Okay, well that's a constant. Okay, that's a constant 0. My y value always goes down as low as 0. Oh, but my y value goes up, and that's not constant. Sometimes it goes up higher, sometimes it goes up a little bit less and less and less. Oh yeah, but it's always bounded by this upper curve. Okay, well I know that one. That's the upper curve of a circle of radius 4. So that's going to be x squared plus y squared equals to 16. Oh, but again, I'm trying to describe y. So let me isolate y here. This will give me y squared equals to 16 minus x squared. Oh, but I want y, so let me take the square root. Normally, I would say I need a positive and a negative square root. But again, here it's clear that since x and y and z should all be positive, here we're not going to take a negative root. We only want the positive value. So here that's going to be the square root of 16 minus x squared, just like that. Okay. So that describes the lowest bound of y, which is constant, and the highest bound of y, which is a circle of radius 4. We only want the upper half of the circle. We want everything to be positive, so here no negative root. Okay, so now we can describe our x value, and remember, the very last boundaries of integration should all be done with respect to a constant. Okay, so here all I want is what is the biggest constant that x ever sees? Oh, well, that's 4. What is the smallest constant x ever sees? Oh, well, that's 0. So that's from 0 up to 4, just like that. So these are our boundaries, and then we have to worry about setting this up. So that'll be the square root of, that's just the number 1, always and forever, plus I can take my function, the one that's defining my surface, that's this one right here, and I can take its partial with respect to x. Okay, so let's go ahead and do that off to the side here. If I have my surface f of x comma y, right, that's given by the paraboloid, that's going to equal to 16 minus x squared minus y squared. If I take the partial with respect to x, well, the derivative of this is 0, the derivative of that will be 0, and I just get minus 2x. If I take the partial with respect to y, I get pretty much the same thing. These will both be 0, and the derivative of minus y squared is minus 2y, just like that. So up here, that's going to be take your two partials, square them, and add them in right here. So that'll be minus 2x squared plus, and that'll be minus 2y squared, just like that. And that is our setup. We can write that as the integral from 0 to 4 of the integral from 0 to the square root of 16 minus x squared, square root of 1 plus 4x squared plus 4y squared dy dx. Okay. At this point, you may look at this and think, ugh. At least that's what I'm thinking. That looks absolutely horrifying. I have the sum of squares, or I have the sum of things inside of a radical, and it doesn't really matter if I had done with respect to x first and then y, or y with respect to x. That's going to be unpleasant. So here, I don't really know what to do with that one in its current position. But in a previous section, we saw that we don't always have to evaluate with respect to just x. Recall back in section 14.3 that we're allowed to change things into polar coordinates. So recall, in section 14.3, we saw that we can convert iterated integrals to polar. And you say, is that going to be easier? No, it couldn't be any harder. But in particular, here I notice that I have my region is described as something that's easy to describe in polar. Namely, it's described as a circle here, or a part of a circle. And here I notice I have squares and sums and differences of squares. Anytime you have squares and anytime you have the square operator in your integrand, or anytime you have circles or ellipses in your as your region, polar coordinates are probably going to be useful. Right? There's no guarantee this is going to be any better, but well, honestly, it's not going to get any worse, right? But no, this actually does will look a lot better in polar. So let's go ahead and convert to polar. Okay. Before we do anything else, remember when you're converting from rectangular to polar, the differential here will introduce an extra factor. So here, instead of dy dx, we're going to have dr d theta. But it won't just change from dx dy to dr d theta, it'll change to r dr d theta. Previously, I called that the Jacobian. We're not really talking about what that means just yet. That's a label for it, which will make sense in a coming section. But for now, just don't forget, when you convert from rectangular to polar coordinates, there's that extra factor of r. So this becomes this. Okay. Now here, x squared plus y squared is equal to r squared. Thinking back to trigonometry. Right? X squared plus y squared, it's going to be r squared. But since that's being quadrupled, okay, well, that'll be 4r squared. So we can write this as the square root of 1 plus 4r squared. Right? And now your boundaries. And you say, okay, well, now I have to convert these things. Well, we could, but that's another reason why it's nice to have these illustrations. Because with this illustration, you note that, okay, how do I describe that with respect to r? Oh, well, let me start with the, no. Just look at the illustration here. This is a circle that got a radius of 4. Oh, so the biggest radius I ever get to is 4. Oh yeah, but I don't want just the points out here. I also want the points a little closer and closer and closer and closer all the way to the pole. Oh, well, at the pole the radius is 0. Oh, so that's just from 0 to 4. R is just from 0, because you're at the pole, out to 4, because you're at the outer circle of radius 4. The angle theta, well, that's 0, and that's pi over 2. Just think about the unit circle, yeah? 0 to pi over 2. And that is significantly nicer than what we had before. So when you set these problems up, a few of them will be doable. Well, actually, many of them will be doable in rectangular. But a few of them, it's going to be simpler if you convert into polar first. And the tip-off to that is, first of all, if you look at this and think, oh, God, that is horrifying, that's a good indication that rectangular may not be the best. But what is even more telling is that in our integrand, we had sums of squares, and our region was a circle or an ellipse or something else that's easy to describe in polar coordinates, a cardioid, an ellipse, a circle, or something of that nature. So now we can go ahead and do this, and let me move that to a different page. Here we're going to abandon the rectangular coordinates, right? That's how we set it up. But once we set it up, we realized, oh, it's going to be easier if we convert this way. So now let's finish off the problem in its polar form. Let's go ahead and have, I'm just going to rewrite I'm going to rewrite the problem from 0 to pi over 2 of the integral from 0 to 4 of the square root of 1 plus 4r squared times r dr d theta. Okay. Remember how this works. Iterated integration starts from the inside working out. So we're going to do that part first, which means that the integral from 0 to pi over 2 remains as it is. And now we're just working on the stuff in the parentheses. Okay, so now I can use substitution here. After all, in fact, let's go ahead and do this off just to the side here. A little side work here. If I want to take the integral, forget about the boundaries, just the integral. If I want to take the integral of square root of 1 plus 4r squared r dr, all right, that's what this is. I could just use a u substitution here. I could say, all right, let u be 1 plus 4r squared, which means du is equal to 8r dr, which is almost exactly what I have right here. Well, okay, I don't have the 8. Okay, so divide that over to the other side. So that'll be 1/8 du is equal to r dr. So then this will become the integral of the square root of, all of this stuff is u, and this extra r, dr, is exactly what you need to form your differential. So here that's going to be 1/8 du. And now if we integrate that, that's going to be 1/8. Here that's u to the 1/2. You can add 1 to that power to make it 3/2, u to the 3/2. But then we have to divide by 3/2, which is the same as multiplying by 2/3. Right? Plus a constant of integration, which when we combine these will give us 1/12 u to the 3/2 plus a constant of integration. Okay? So here, that's what our antiderivative is. You say, well, yeah, but that's in terms of u. Okay, plug your r back in. Here, u is equal to 1 plus 4r squared. So here, my antiderivative is going to be 1 over 12 times u, which is 1 plus 4r squared, right, to the 3/2 power. Here I don't need to worry about a plus c because, of course, that's a constant, and when I have a definite integral, that won't really matter. Here, what I'm going to do is I'm going to write this as r equals to 0 and r equals to 4. It's a nice habit to get into when you have multiple integrations. It's really easy to confuse yourself and say, oh, wait a minute, I forgot what I was about to plug in. You're plugging in r equals to 0. Here you're plugging in r equals to 4. Okay. And now, because r is the only variable, this whole thing will become a constant, which is definitely a lot simpler than the other integration which we might have done with the xy coordinate system. So this is now the integral from 0 to pi over 2 of, and I'm still in the parentheses. If I plug in 4 right here, 4 times 4 is 16, times 4 is 64, plus 1 is 65. So it's going to be 1/12 times 65 to the 3/2 power. If I plug in 0 right here, that's going to be 0 plus 1 is 1. 1 to the 3/2 is still 1 times the 12th. So it's going to be minus 1/12 like that. D theta. Right? Plug in 4 gives me that. Plug in 0, well, that whole thing becomes 1, so that just gives me the 1/12. And now that's a constant. And if I want to take the integral of a constant, it just becomes the constant times the variable of integration. So this is now 1 over 12 times, here let me factor out a 1/12 just to make this a little cleaner. This is going to be 1/12 times 65 to the 3/2 minus 1. Right? The 12 is my denominator. 65 to the 3/2 minus 1 is my numerator. And that's times theta, because I've integrated with respect to theta, evaluated from 0 up to pi over 2. Let's see here. If I plug in 0, the whole thing is 0, so who cares about that one? In the end, all we need to do is worry about plugging in pi over 2. So this will give me 65 raised to the 3/2 power minus 1 over 12 times pi over 2 for a grand total of, let's see, 65 to the 3/2 power minus 1 times pi over 24, which is only slightly painful compared to what might have otherwise happened if we had left everything in rectangular. All right, so here, let's take a look at another example here. We're going to go ahead and find the surface area of, and let's give our region as an illustration. So let's see here. Find the surface area of f of, well, let's just say z. So that looks just like the last one. So that z is equal to 9 minus x squared. Oh, you know what? That's actually one of your homework problems. So let me do one that's the one right after that. That way you have something to compare it to. So let's try z is equal to y squared. Now this is a function of two variables, but here your x is missing, which is going to be telling you something here in a moment. So z is equal to y squared, and that is defined over a square that has the vertices uh, 0, 0, 3, 0, 0, 3, and 3, 3. So in other words, it's just this square here that goes from the origin up 3 steps, right 3 steps, just like that. Okay, so here we don't really have anything that's nice to describe in polar coordinates. Same thing here, it doesn't look like anything particularly useful or simple in polar coordinates. So this one will probably be done in rectangular, but again, you never know. Sometimes it's hard to tell ahead of time. So go ahead and give this a try. Go ahead and pause the video and see if you can find the surface area of this surface over this region. Once you have an answer, go ahead and unpause and we'll go through it together. All right, well, it looks like the description of this region is trivial. It's a rectangle. So x goes from 0 to 3 and y goes from 0 to 3. So here, this isn't really the complicated part. It's let's make sure we set everything up correctly and then start the integration. All right, so we know that our surface area, and here I'll write SA for surface area, is equal to, we're going to take the double integral over the region R, which again, that'll be trivial to describe in just a moment, of the square root of 1 plus f sub x at x comma y quantity squared plus f sub y at x comma y, again quantity squared, dA. All right, well, we can take the derivatives of those. So that's going to be the double integral over r of the square root of 1 plus, with respect to x, that's 0. All right, because here there is no x, which means this is constant with respect to x. And the derivative of any constant will be 0. On the other hand, here the derivative with respect to y will be 2y. Okay, but don't forget to square that, just like this. And so this gives us the double integral over r of the square root of 1 plus 4y squared dA. Now, at this point, you may be concerned with the fact that that looks somewhat unpleasant. That looks like it's going to require a trig substitution. If you think back to Cal 2. Well, yeah, but that's only if you start by integrating with respect to y. You don't have to start with respect to y. We're doing a double integral, which can be done by an iterated integration, and iterated integration can be done with respect to either variable first. So if I integrate with respect to y first, yeah, I'm going to need some kind of trig substitution. But if I integrate with respect to x first, maybe something nice will happen in the interim. All right, so or not. Yeah? It may just require us to do the substitution. All right, well, we'll see. Here, let's go ahead and write this as the integral. And here I'm going to go ahead and use Fubini's theorem to write this with respect to, and I'm going to do it with respect to x first, because I realize if I do it with respect to y, I have no choice but to do something complicated. If I do it with respect to x first, maybe something works out nicely, or maybe not, but either way, we give it a try. So let's see here, that's going to be the square root of 1 plus 4y squared. I'm going to do dx first and then dy. I realize x goes from 0 to 3. Okay, so 0 to 3. And here y goes from also 0 to 3. Oh, that's the nice thing about rectangles. Everything's constant. Okay, so now let me go ahead and perform this in this first integral here, which means the outer integral remains just untouched for now. This is going to be the integral from 0 to 3 of some stuff dy. Okay, so now let's go ahead and do the stuff in there. Well, that one's nice because here that's a constant with respect to x. So this whole thing just becomes that constant times x. Okay, so that's going to be square root of 1 plus 4y squared times x. And that's going to be evaluated from 0 up to 3. And again, that's x equals 0 up to x equals 3. And we can substitute in these values. Of course, substituting in 0 makes the whole thing 0, so we don't worry about that one. But if we substitute in 3, that's going to be the integral from 0 to 3 of, well, let's see, that's 3 times that radical. 3 square root of 1 plus 4y squared dy. And I realized that, well, that didn't help at all, right? Oh, well, we tried. So here, it does look like we're going to have to use a substitution here. So let's go ahead and go off to another page, and we will integrate the integral from 0 to 3 of, let's go ahead and adjust that slightly, there we go. The integral from 0 to 3 of 3, let me go and pull the 3 to the outside since it is a constant, square root of 1 plus 4y squared dy, just like that. Okay. And, well, now we use our Cal 2. Because now we can look at this and say, okay, that's the sum of squares inside of a radical. That's a trig substitution. So here, let me take, this is the sum of two squares, so that's going to be tangent. Here, the thing that you square to get your variable squared, that's what you call u. So u in this case, so u squared in this case is 4u squared, which means that u is equal to 2y. 4y squared, 2y. Our a squared is just that constant, which means our a is just, again, the square root of 1, which is 1. So u squared is the variable, a squared is the constant, and then from those squares you can find the u and the a. And then your substitution is the following. Your substitution is, let's see here. Your substitution is u is equal to a times the tangent of theta, which for our problem, u is equal to 2y. A is equal to 1, so let's not worry about that. Tangent of theta, just like that. Okay. Here, we can divide both sides by 2, which would give us y is equal to 1/2 times the tangent of theta. And now we could use this to find our differential. If y is equal to this, then dy is equal to 1/2 secant squared of theta. All right. So now over here, we can write that as the 3 stays a 3 integral of the square root of, well, that 1 is a 1. It stays constant, just like that. But our 4y squared, that's going to be the square of the tangent. All right. If 4, so this is 2y. We don't want 2y. We want 4y squared. So that's going to be the square of this. So here that tells us that 4y squared is equal to tangent squared of theta. So here that's going to become plus tangent squared of theta, like that. And then over here, I'm going to take the dy, my differential, and that is now 1/2 secant squared of theta. So let me take the 1/2 and pull it to the outside, and that leaves me just secant squared of theta d theta. Okay, 1 plus tangent squared of theta, that's a Pythagorean identity. So that's going to give me 3/2 the integral of the square root of the secant of theta squared times secant of theta squared d theta. Here, the square of the square root just gives me secant of theta, so that's 3/2 the integral of the secant of theta. Over here you have secant squared of theta d theta. And this gives us 3/2 the integral of secant to the third of theta d theta, like that. Your boundaries, you can just go ahead and substitute. After all, here we were starting with y goes from 0 up to y equals 3. Well, yeah, but right here, that's y equals to 1/2 tangent of theta. So from here, if y equals to 0, then that means 1/2 tangent of theta is equal to 0. After all, y and 1/2 tangent of theta are equal to each other. So if that one's 0, so is that one. Okay, but now that tells us that theta must be 0, right? Double both sides, tangent of theta is still 0, and if the tangent of theta is 0, that means theta must equal to 0. Okay, so my lower bound is still 0 for all of these. Let's talk about my upper bound. If y is equal to 3, then that means that 1/2 tangent of theta is equal to 3. After all, y is equal to 1/2 tangent of theta. Those are the same. Let me double both sides. So that'll give me the tangent of theta is equal to 6. And so that means that theta is equal to the inverse tangent of 6. Like that. So here, I can go ahead and give myself an upper bound of the inverse tangent of 6. Of course, you didn't have to change your boundaries. You could have found an antiderivative and then come back in terms of y and evaluated using these original boundaries. But here, that'll save you the extra 2 or 3 steps that are required to do that. At the end, we won't have to come back to y. We'll just evaluate with respect to theta. Okay, so now all we need to do is find the integral from 0 to the inverse tangent of theta of secant to the third of theta d theta. And here, let's just go ahead and do this off to the side. Let's go ahead and find the antiderivative of the secant cubed of theta d theta. Okay? Once we have that, then we'll just be able to plug in our endpoints and get our result. So we can integrate this one. This one is a slightly longer integration by parts problem. Here, we can go ahead and split secant cubed as secant times secant squared of theta. So let's go ahead and do that. Secant of theta times secant squared of theta d theta. And now we're going to take this and we're going to call this our u. Okay, so u is equal to secant of theta, which means that du is equal to the secant of theta times the tangent of theta. Okay, and now our dv must be whatever's left. So that's secant squared of theta d theta. Oops, I forgot a d theta there. And so our v must equal to the antiderivative of secant squared of theta, which is tangent of theta. So now by the integration by parts technique, this integral is going to be u times v. Okay, so secant of theta times tangent of theta minus the integral of v times du. Oh, that's secant of theta, tangent of theta times another tangent of theta. Okay, so that's secant of theta tangent squared of theta d theta. Multiply these two together. Okay, well now tangent squared of theta, we've already seen in a previous part that we can change into secants of theta using the Pythagorean identity. So here we can write this as secant of theta times tangent of theta minus tangent squared of theta can be written as secant squared of theta minus 1. So I'm going to bring that one down. And now this tangent squared of theta, I'm going to write this as secant squared of theta minus 1. That's the Pythagorean identity from here to here. I can distribute this, and that'll give me secant of theta times tangent of theta minus the integral of, if I take secant of theta times negative 1, I get negative secant of theta. If I take secant of theta times, and that's a positive, times secant squared of theta, I get plus secant cubed of theta d theta. All I did here was I distributed there and there. You notice I wrote that one first, and that's just for convenience. In the next problem here, I want some stuff to cancel. If we wrote it the other way, it's still the same. So negative secant of theta plus secant cubed of theta. Okay. Here, let me go ahead and distribute that negative. So that'll give me secant of theta tangent of theta plus, and that's why I wanted that one first, so that I could have that positive in the front. That's plus the integral of secant of theta minus secant cubed of theta d theta. All right, so distribute that, makes that a positive, makes that a negative. And now I can split this because of the linearity property of my integral. So here I can write this as the integral of secant of theta d theta minus the integral of secant cubed of theta d theta. All right, so that one, the integral of that one minus the integral of that one. And that's a 3 right there, cubed. Okay, but now we're almost done, because notice that is the same as our original problem. So here I'm going to just write this all the way down, secant cubed of theta d theta. Okay, so every one of these is equivalent. All right, but now that means that I can take this one and bring it over here and combine my like terms. So if I now add the integral of secant cubed of theta d theta to both sides, this is gone, and I'm left with double the integral of secant cubed of theta d theta is equal to, that's just secant of theta times tangent of theta, plus, and this integral, the integral of the secant of theta, that was one of our elementary integrals from Cal 1, that's the natural log of the absolute value of secant of theta plus tangent of theta, just like that. We see that at the very end of Cal 1, plus a constant of integration, of course. And finally, if I divide both sides by 2, I get that the integral of secant cubed of theta d theta is equal to 1/2 secant of theta times tangent of theta plus 1/2 the natural log of the absolute value of the secant of theta plus the tangent of theta plus a constant of integration. Right? So that's our antiderivative, which means up here, that's what we're going to pop in. All right. So then that's going to give us, we don't need that constant of integration here because, of course, we only have a definite integral. And here the constant of integration will cancel out. So coming up over here, that's going to be 3/2. And I can distribute the 3/2 across these numbers, right? After all, that's just the integral on its own. But I want 3/2 times the integral. So let me distribute 3/2 amongst these. And that'll give me 3/4 secant of theta tangent of theta, all right, plus, and that's also going to be 3/4, the natural log of the absolute value of secant of theta plus tangent of theta. And all of that's going to be evaluated from 0 up to the inverse tangent of 6. From 0 up to the tan inverse of 6. All right. And that about does it. At this point, it's just a matter of substitution. We're going to plug in theta is equal to this number, plug in theta is equal to this number, and go ahead and subtract. Note that if you plug in 0, the tangent of 0 is 0, so that one goes away. Here, the tangent of 0 is also 0. The secant of 0 is 1. 1 plus 0 is 1, and the natural log of 1 will be 0. So plugging in 0 here will make this 1, which makes this whole thing 0. And plugging in 0 here will make that 0, so that entire thing will be 0. So 0 plus 0 is 0. So really the only one you need to plug in is that number there. So that'll be 3/4 the secant of the inverse tangent of 6 times, here you have the tangent of the inverse tangent of 6, which is just the number 6, right? The tangent of the inverse tangent, those are inverse operations. Since they both have an infinite, since the tangent inverse has an infinite domain, here we can just pop in that number. So here we have 6 plus, And then we have 3/4 times the natural log of the absolute value of, you can take the secant of the inverse tangent of 6, and again, plus the tangent of the tangent inverse of 6, well, that's just going to be 6. Okay, and there we go. At this point, you could, you pop that into a calculator if you want, give yourself a decimal approximation, or hell, even one step above, you pop that in and give yourself a decimal approximation. Right? So that is our result, and that is the end of our section. These problems can be a little long, but that's entirely due to the integration. When you start having double and in a bit triple integrations, oftentimes it'll be convoluted by the fact that one or more of your integrals may be difficult. It's possible that one of your integrals is nice, so is another one, but the third one is difficult. And, well, that's just something we have to handle. That's why Cal 2 puts such a heavy emphasis on methods of integration. Because when you have multiple integrations, as we saw before, we may be able to convert into polar to make things simpler, but in other cases, conversion into polar isn't really an option. In particular, when you have boundaries which are not curved at all, which are straight. In which case, well, you may have one of your integrals, which is nice and easy to perform, but the other integral is something a bit more difficult. So the thing to take away from this section is the setup. We had our definition for a definite integral, for a surface area, and that's given by a double integral, not definite integral. It's given by a double integral over R of this expression here. If you can set that up, all that's left is integration, which of course may not always be the simplest, but at least it's something that we are experienced in. So that's the end of the section. As an assignment, you may wish to try section 14.5. Go ahead and do numbers 1 through 17 odd. Okay. If anybody has any questions, comments, problems, please reach out to me, contact me, and I will help you as I can. And I hope everybody has a nice day.